Let's practice drawing some E2 mechanisms. So first problem, we've got 4 different reactions. All of these we're going to draw a mechanism for the E2 reaction. First thing that we want to do with these types of problems is identify the carbon that holds the leaving group. In this reaction, we're going to begin by abstracting, using the base here to abstract a hydrogen atom, not from the carbon that's holding the leaving group, but from one of the carbons that is attached to it. So there's 2 possible places where we will do our hydrogen abstraction. And so what I want to do is draw the hydrogen atoms in on both of those carbons. Now, the actual location, like which hydrogen atom is going to be abstracted, is dictated in part by the base that we're using for the reaction. This base right here, OCCH3, this is tert-butoxide. Tert-butoxide prefers to abstract a hydrogen atom from the least substituted carbon, talking specifically about the carbon atoms that we're focusing on. This carbon atom right here is tri-substituted, or a tertiary carbon. I don't know why I went out of number order there. 1, 2, 3. So this right here is a tertiary carbon. This carbon is a primary carbon. It only has 1 carbon attached to it. And that means that this bulky base is going to prefer to abstract from this particular site. So our bulky base is going to go after one of these hydrogen atoms. The carbon-hydrogen bonding electrons are going to come in to make a carbon-carbon double bond, and the leaving group will leave. Nothing happens at all out here with this other hydrogen atom. That's not going to be involved in this reaction. And then the product of this reaction is going to look like this, where we are placing a double bond in between the 2 carbon atoms that were involved in this reaction. Let's practice again. So we're starting with the same molecule, but we'll go through the same process. First thing we want to do is identify the carbon holding the leaving group, and the next thing we want to do is identify the carbon atoms that are adjacent to it, or attached to it. Now we want to think about where this reaction is going to take place. Here we are using methoxide, OCH3. It is not our bulky base. It's not tert-butoxide. Anything other than tert-butoxide, so for example, methoxide, this base is going to prefer to abstract a hydrogen atom from the most substituted carbon. So again, keeping in mind with what we have going on here, we've got 1 hydrogen atom on that left-hand carbon, this guy right here. This carbon atom is tertiary because it has 3 carbons attached to it. And then this guy over here, this is a primary carbon because it only has 1 other carbon attached to it. Because this is not tert-butoxide, that means that it is going to abstract a hydrogen from the most substituted carbon. The carbon-hydrogen electrons will come in to form a carbon-carbon double bond, and the bromine will leave, and that gives us this product right here. Now we're going to try it again. We've got 2 more examples. First, we want to identify the carbon that's holding the leaving group. It's an iodine. And we want to identify all of the carbon atoms that are bonded directly to it. We'll go ahead and do both of these at the same time. And we want to draw in all of the hydrogen atoms on those highlighted carbons. Any one of these hydrogen atoms is eligible to be abstracted in this reaction. So looking at the first reactant, we have OET. This is ethoxide. This is not the bulky base. That means that it wants to grab a hydrogen from the most substituted carbon. So anything other than the bulky base is going to grab a hydrogen from the most substituted carbon. This carbon atom right here has got 2 carbons on it, so it is secondary. This carbon atom only has 1, so it's primary, and this guy right here is also primary. So that means that this base is going to grab one of these hydrogens. We're going to break the carbon-hydrogen bond, move the carbon-hydrogen electrons in to make the double bond, and we're going to get rid of the leaving group, and that's going to give us this molecule right here. We have formed the double bond in this place right there. Now for our next example, we have the same alkyl halide, but this time we're dealing with the bulky base, which means that we're going to be going after a hydrogen atom that is on the least substituted carbon. So those are going to be the 2 methyl groups right here. Now you might be wondering, ooh, which one should I choose? Let's just kind of pretend like you don't know what to do here. Let's just pretend like we've got 2 different options. So let's grab this hydrogen, break that bond, get rid of that leaving group, and we have this alkene formed. And then the other possibility would be, let me kind of erase my little arrows here real quick. The other possibilities would be if we grabbed one of the hydrogens on the other methyl group, broke that bond, got rid of that leaving group, and that would give us this guy right here. Now the question is there a relationship between these two products, or what is the relationship between these two products? Sometimes it can be kind of hard to tell what the relationship is between the two of them, but if you use some sort of numbering system, like as if you were going to name these molecules, if you try to find some sort of consistency in the numbering, like let's say that we are going to call that double bond carbon 1 and carbon 2, and then we can see on carbon number 2 we're going to go to 3, 4, 5, 3, 4, 5, like that, and then we've got this bonus methyl group on carbon number 2. By numbering these, we can see that these are identical molecules. They're just drawn in two different ways. In that situation, first of all, it's not going to matter which mechanism we draw, whether we show the attack here or whether we show the attack here, because it's producing identical products. Second of all, you don't want to draw both of these molecules. You don't want to draw the same molecule twice, basically. Okay, so now we're going to label all of these products as Sate-Sef or Hoffman products. The Sate-Sef product is the most substituted alkene, and the Hoffman is going to be the least substituted alkene. And so that's going to come from comparing not all four of these to each other, but comparing the two products that came from the identical reactant. So comparing these two to each other. When we're doing this sort of a thing, we want to look at our double bond, and then we want to ask ourselves how many carbon atoms are attached directly to that double bond. So looking at this double bond, we have one carbon atom that's directly attached. This is going to be a mono-substituted alkene. And then same thing for this one down here. Here's our alkene, and we want to ask ourselves how many carbon atoms are bonded directly to that alkene. This one has 1, 2, 3 carbon atoms bonded directly to it. So this is our Sate-Sef product, and this is our Hoffman. And then for our next two down here, comparing these two, this is our least substituted. So there's our Hoffman, and this is our Sate-Sef. Now, what I've gone through for all of these, what I've gone through and drawn is simply the major product for all of these. In most instances, that's all that you're going to be asked to draw, just what is the major product. But if you're in a situation where you're being asked to draw all the products or draw the major and the minor products, then we want to take into consideration the other products that could be formed. So when we are using the bulky base, the major product is the Hoffman product, the least substituted product, but we do see that we get a little bit of the Sate-Sef product being formed. So we'll just kind of add this up here, like because this in small amounts, this guy is also being formed. So here is a minor product. And then we have the opposite being true for this reaction down here. When we're using not a bulky base, our major product is the Sate-Sef product, but we are also forming a very small amount of the Hoffman product as well. So we'll add this guy down here, and we'll say that this is our minor product. And then we'll kind of do the same thing down here. For this reaction, let's copy this guy up here. So we're going to get a little bit, when we're using that small base, we're going to get a little bit of the Hoffman product. And then last but not least, now all of these reactions were kind of set up strategically so that we didn't have to worry about cis and trans or E and Z, but that is definitely coming. Next problem, cis and trans is based on the stability of the alkene. Practice drawing the mechanisms and predicting all possible products, and then identify the major and the minor. So let's begin by finding the carbon atom that has the leaving group. OTS, tosylate, is a great leaving group. And here are the two possible carbons that are eligible for elimination. Here are the hydrogen atoms that might get abstracted by this base. We are dealing with the bulky base, which means that it's going to go after a least substituted carbon. This is a secondary carbon. This is a primary carbon. That means that our bulky base wants to attack the primary carbon because it is least substituted. It's going to give us something that looks like this. And this will be our major product. Now this did say to draw all possible products, so there's my major product. But what I'm going to do is draw the minor product, which would come from the bulky base grabbing one of the carbon atoms from the secondary carbon, like that. So that would give me a product that looked like this. And this is minor. Now, after we've drawn all possible products for an elimination reaction, we should always look at them and ask ourselves, ooh, is it possible for me to draw a cis isomer or a trans isomer? This molecule does not have a cis or trans isomer. This molecule, we've drawn the trans isomer, which means that there is a possibility that the reaction would form the cis product instead. This is also going to be a minor product. So out of all three, this is the thing that we're going to make the most of. Now this reaction, or this question, is asking us to identify the major and the minor, and we've got two things labeled as minor. So let's go ahead and decide which of these two is going to be the most minor, the one that will produce the least of. And we're going to do that by comparing the stability of these two alkenes. We've talked before about how a trans alkene is more stable because the R groups are able to spread out. A cis alkene is not quite as stable because the alkyl groups are more crowded. Because this is less stable, that means that it is the most minor product. So I'm just going to take the label off of this guy. We don't have a name for this. We can only identify the one major and the one minor, and then the things that are in the middle don't get a name at all. We've got one more of these that we can practice. Here's our carbon that holds the leaving group, and here's the carbon that's attached to it. Here's another carbon that's attached to it, but only one of those carbons has hydrogens on it. So this carbon right here, we can see that it has 1, 2, 3, 4 bonds, which means no hydrogens on this guy, not eligible for the E2 reaction. We only have one hydrogen available. That means we don't really have to think about where this reaction is going to take place. There's only one place that it can occur. That's going to look like this. And that will give us a product that looks like this. So here it is, and this is the only product that we're making. We're putting the carbon-carbon double bond right here in this spot. Now, before we get excited, we have to ask ourselves, what about cis and trans? Could I draw this molecule in a different configuration or a different stereochemical orientation? And we can, absolutely. So we could change it so that right now the methyl group and the benzene ring are cis to each other, and I've drawn it now so that the methyl group and the benzene are trans to each other. And we need to decide which of these is major and which of these is minor. This one's a little bit trickier than up here. We're looking at that line between of the carbon-carbon double bond, and basically what we want to do is minimize crowding or minimize steric hindrance. We have this big, huge aromatic ring, and what we want to do is put it adjacent to something that's nice and small, that takes up the smallest possible amount of space. Methyl group versus an ethyl group. This guy is way bulkier and way more crowded, so this molecule is experiencing a lot more steric hindrance. We're going to label this as a minor product. We'll call this a major product. Now, there are more problems on this worksheet, but we're going to save the rest of these for another video.